Okay, so it's week 10. It's Tuesday. So this is lecture 19, and let's just get into chapter 7 on wind. And also, don't let me forget that in the third of the lecture, I want to get into summary 4 as well. Okay, so let's just hop right into the figures for chapter 7. First of all, a little bit of terminology. The difference between a wind turbine and a windmill, a lot of times you'll hear people call wind turbines windmills. A windmill is something that is just taking mechanical energy and turning it into some other mechanical energy. So like a windmill could be used to pump water, for example. A windmill could be used to crush grain. A windmill might be used to, gosh, one thing I'd love to see it being used as just spin a big blade for shredding plastic or other recyclables, sort of as a dump load. But a wind turbine or a wind generator is something that's making electricity. So it's going from mechanical energy, which is the wind blowing, to electrical energy, which is electrons flowing through wires. All right. And there, as we will shortly see, there are about as many different types of wind turbines as the human mind can imagine. It's unbelievable, all the different designs that have come out there. I myself have designed one with some students, applied for an international patent, only to realize that there was a firm in California that sort of beaten us to almost the identical design. So you might think, hey, I've got something super original no one's ever thought of. Well, chances are there's some other entrepreneurial person out there doing the same thing. Okay, but let's see what Derek Taylor has to say about it here in chapter 7. The first figure is figure 7.1. And I'm just going to read from the book for a second. It says, for many years, small-scale wind turbines have been manufactured to provide electricity for remote houses, farms, and remote communities, and for charging batteries on boats, caravans, and holiday cabins. Thousands of small turbines, similar to that shown in 7.1, are in use worldwide. And that's just a 70-watt job. It's kind of hard to put the scale on just 70 watts, but our own turbine back in the bullpen, it's a kilowatt. I mean, it's over 10 times more powerful. So this must be either much smaller than it looks.
Its actual size.
It's maybe like, or the generator wasn't built that well. But 70 watts. This thing's probably just like a foot in diameter. I mean, it's almost like a little toy. It's 70 watts. But on the other hand, in my opinion, like just something's better than nothing. Better to have just something out there making some renewable energy rather than relying on fossil fuels. Okay, so since the 80s, the technology's been mature, enabled the rapid growth. Between the 80s and late 2000s, the cost has fallen steadily and significantly, and the capacity has gone up greatly. So, as we'll see shortly, it's usually to your advantage to have a turbine that's higher up in the air where the wind's blowing faster and steadier and more predictably. It's also a matter of the economy of scale. So if you're going to build a turbine, building a turbine that's twice the size typically does not cost twice the amount of money. Building one that's 4 times the size is not going to be 4 times. You're going to put the time and the effort into building one. How big can you build it, thus getting access to more and more energy without, so that you get to a place where it becomes more cost effective. All right. Let's see. So it says here also in the book, as an overview, 7.1, a total of over 194 gigawatts of wind had been installed by the end of 2010, with 36 gigawatts added just that year. So this industry is growing by leaps and bounds. So 194 gigawatts, that's a fifth of a terawatt. If you remember, humanity's running at 16 terawatts. I wouldn't be surprised if there's, close to a terawatt installed already by now, pretty close to a terawatt. Now, does that mean that we're always going to get 1/16 of our energy from wind? No, that's just the capacity. These things, the wind is not blowing 24/7, 65. Okay. So, growing all the time. Now, let's just look at the physics of the wind here. These are the global wind circulation patterns. So the green that we see there are more or less the jet streams. There are, in fact, some companies working on tapping the jet stream for renewable energy, believe it or not. They're not always blowing in that one same straight pattern, but that is the direction that the wind blows, and that's more or less higher elevation winds. The pinks, or the purples there, second down, are what are called the westerlies, and they're blowing from the west to the east. The trade winds, they were named. There's a little bit of a deal here on box 7.1. It says some of the air that reaches the surface at these middle latitudes is forced back towards the low pressure zone at the equator. These movements are known as the trade winds. So you can imagine if you were doing trading in the Atlantic Ocean and you needed to get from west to east, these orange surface winds are what's going to blow you in that direction. And then the Hadley cell is also mentioned there. By George Hadley, first described them in 1753. Another thing to note here, that one thing the authors are trying to depict are the three-dimensional nature of what's going on. So you can see this particular portion of the Hadley cell. You've got the surface heating around the equator. This hot air is more or less going up, from the equator, reaches higher elevations, cools down, and you sort of get this circular motion, if you will. You can also see in this case, this hot air comes up, interacts with the jet stream, and then heads off in this direction, and then other related phenomena going on in the Ferrel cell and the polar cell. And these are, roughly divided out into 30-degree increments. So the equator being at 0, the Hadley primarily occupying 0 to 30, the Ferrel 30 to 60, and then 60 to 90 are these polar cells, some of which are blowing east, some of which are blowing west. Another thing worth mentioning here, it says there's a further complication in that because the Earth itself rotates, winds moving across the surface are subject to a phenomenon known as the Coriolis effect. This is the net result of this effect given that the Earth rotates in an eastward direction. So obviously this big pink line is showing you the direction of the Earth's rotation. Earth rotates in the eastward direction, is that in the northern hemisphere, northbound winds tend to veer to the right. So as the Earth rotates this way, any wind that's going that way sort of appears to be heading to the right along with the direction of rotation, and just the reverse is true in the south. You don't typically think of air as having momentum, but it does. And it's obviously, and I think when we were going over the tidal exercises, we talked about the fact that right at the surface. So in the tidal, right at the surface, or in the case of waves too, there's really zero velocity right at the surface. We have a fluid interacting with a solid. The higher you get, the greater the velocity is. So in this case, once the wind is that high, it's still got those shear interactions of the two layers interacting with each other, but it diminishes the higher you go. The air is less dense, so that you've got the two interactions. One is just the friction of the wind with itself. The other one is just whatever momentum it had when it sort of started its journey. So those two different forces affect all of the flows that we're seeing here. Okay. Atmospheric pressure is mentioned. So 1 bar is the level of atmospheric pressure. It's also 101 kilopascals. 1 pascal, this is worth noting. Chapter 7. So pressure. This is actually a pretty good tie-in with our physics we've discussed up to this point. 1 pascal equals 1 Newton per 1 meter squared. And the thing, and so 1 atmosphere also equals 1 bar equals 101 kilopascals. And so what that means is that there are 101,000 newtons per square meter of pressure. And the other thing to note about atmospheric pressure is that it's, well, it's just like water pressure. It's really acting more or less the same in all directions. This is assuming the wind is not blowing. But the reason that this 101,000 newtons per square meter, so here we are sort of, standing down here, isn't squishing us, is because there's pressure from all sides, and it's equilibrated. Only when you have a delta P, a change in pressure, do you in fact get wind. Where do you get a delta P from? Well, you get a delta P from a delta T. And I'll just write that out as well. So if we have P V equals nRT, this you can think of as the volume of a chunk of air. And this could be the volume in the room, it could be the volume over a city. But if you look at this equation, you see, if the temperature changes, the pressure is going to change as well, or the volume. One or the other is going to happen. So in general, when the temperature goes up, and this is where it gets a little bit tricky. In general, the temperature goes up, the volume, like one of these two things has to change, either the pressure or the volume. One of them's got to go up. Well, if the pressure is the same, if there's no extra atmosphere around, the air will literally get bigger. There'll be less space in between the molecules. When that happens, it becomes less dense, the air rises, and that's what leads to these vortices and the movement. So really what's driving all of these is a change in temperature right there. And I want to show you one more thing. This is not going to be on the exam. Levi, you might have seen this in the past, but if you look at the Navier-Stokes equations, there's something down here. Yeah. Oh, this is actually a little more intense. Incompressible. There's two different versions. One is compressible, and one's incompressible. Momentum equation. Yeah. So in this case, this U that you see in here, and again, this is just kind of food for thought. Let me just make sure I've got all the variables straight. Yeah. This U is actually the velocity vector. So, velocity itself, so we'll go back to this picture. In this case, you're like, well, which direction is the wind blowing? Well, normally we think, okay, it's blowing either east and west or north and south. Well, if it's blowing northeast, you have to see, how much is in the north direction, how much is the east direction. Well, it also might be blowing up a little bit. So there are three different components to your velocity. This is telling you how quickly the velocity is changing. So if the velocity is accelerating, this is positive. If it's decelerating, it's negative. This is telling you, this is at a certain point, this is telling you how fast it's changing with respect to time. This guy right here is telling you how fast it's changing with respect to space. So you're going to have the wind might be blowing really crazy over on one side of town and not at all elsewhere. This is the density of the air. So as I just mentioned, warmer air in general is less dense. This is the pressure, so the change in pressure, and the pressure is changing all the time. This is the viscosity of the air. So again, just kind of going back to hand puppets, how maple syrup versus, air. The maple syrup has higher velocity and it interacts with itself more in a shear direction. And then this is gravity. So the reason for all these del operators is taking into effect that the velocity itself is not just a number, it's a vector. So this guy, you throw all this into an atmospheric model, throw in some temperature, which is going to change this density, and this is what makes the wind blow. So, and if you're doing a dissertation in meteorology, you would dig pretty deeply into this. If you were trying to do some intense weather pattern modeling, this is where you'd start for doing your model. Okay, so there's kind of some of the physics or the science of wind. Now, how do you measure pressure? Well, one way to do it is just to have a vacuum up top and a big bubble of mercury or some other fluid on the bottom, and the mercury itself, this head of pressure right here wants to, gravity is more or less forcing this column down into this ball of mercury. The only thing that's keeping it from going all the way down is the fact that you've got a vacuum here, or more or less a negative pressure pulling it up. So obviously, if the atmospheric pressure goes up, there's more force going back to our little equation, there are more newtons per square meter on the open surface. So this is open to the atmosphere, More atmospheric pressure pushes down, and the mercury rises. And so a lot of times you hear, oh gosh, the pressure just dropped. That means that there's now a relative vacuum for all the water for a storm to move in. So and you hear people say, oh, my rheumatism's acting up, the pressure dropped, there's going to be a storm, what have you. Okay. Yeah, let's take a look at this. Another really important thing to note, and then we'll take a break here, because I think we're pushing. Yeah, no, we're in good shape. Let's look into the energy and the wind. This is critical. This is also one of those rare occasions where the authors have bothered to number their equations in the book. I like that. Okay. So we can start, and I'm on page 300. So we can start with energy kinetic equals 1/2 mv squared. So m is mass, v is velocity. Now what we're going to do next is we're going to change mass into density times volume times v squared. Right, so we know off to the side over that mass just equals density times volume. Now, in this case, what volume are we talking about? And I think sometime we'll do this little problem in NRGY 101. But so here's your turbine sitting inside here. This is little v for velocity. All of this junk in there is big V for volume. So just imagine a big cylinder of air blowing past this turbine, which of course is then spinning, and rho, in the case of air, is about 1.2 kilograms per cubic meter. Okay. So the volume is just the area. That's the area of the cylinder, of the base of the cylinder, times some height. Or some length, however you want to think about it. Whatever volume of air is basically the cylinder. It's got an area, it's got a height. So we'll keep writing. Equals 1/2 rho A H v squared. So far, so good. E kinetic. All right. Now, let's go ahead and see if we can't get from energy to power. Because we know that power equals energy divided by time, right? So all I'm going to do is just divide both sides by time. So now I got power equals 1/2 rho A H v squared. Now, I kind of snuck in my 1/T on this side. I put in a 1/T and I came up with power. I'm going to sneak the T in right there. I kind of put it wherever I want, but I'm going to put it right there under the H. And magically, this H, which was just the distance or the height of the cylinder, now simply becomes velocity. Maybe a little bit of a mind bender, but just think about a little molecule of air sitting right here at time equals 0. It blows along through the turbine, ends up here at time equals 1, and the velocity just equals the change in height, in this case height is horizontal, that's okay, times the change in time. So we managed, through the power of algebra, to turn to combine space and time and turn it into velocity. So now we just have the power equals 1/2 rho a v cubed. And that, I believe, is equation number 2 in your textbook. So they don't derive it quite in the same way. Hopefully the way I've described it here sort of shows you where that comes from. So if you want a more powerful turbine, what can you do? Well, you can't really make the air more dense. You can make it bigger. That's why we see these giant wind farms. You can't really make the wind blow faster, but you can see since it's velocity cubed, the higher you get that thing, typically the faster the wind's blowing and there's more bang for your buck. So that's one of the more important equations you're going to see in this chapter in terms of, what's the power of the wind? Well, there it is. Okay. All right. Now we're looking at typical weather patterns showing high and low pressure. And the numbers that we're seeing there, those are actually in, well, they're not really in kilopascals, are they? If there were a decimal point right there, so 101.3, that would be 101.3 kilopascals. 992, this would be, let's write it out. Let's write this guy out. So 1013 translates to 101.3 kPa, translates to 101,300 PA, right? Let's take another one. 992 translates to 0.992. No, I'm not doing this right. Hang on. Oh, yeah. This is where my visual memory and my numbers going to get done. Yeah, 99.2, exactly. I knew if I wrote this out, I'd be able to go, okay, KPA gives you 99,200 pascals. There we go. Okay, so the way the meteorologists want to see is like just kind of these 3 or 4 numbers. The take home here is that, well, if we divide it as a percentage, so let's see the percentage here. So 101,300 minus 99200 equals, divided by 101,300 equals, we're looking at about a 2% change in pressure. And so, relatively small change in pressure over a relatively large difference. But it is these changes in pressure that drives the wind. And you can, I think, appreciate that when you have greater extremes in temperatures, from some of the climate change models, you're going to get greater extremes in pressure gradients and therefore greater storms and winds and all that. So that's why the climate change folks talk their thing. It's not just, okay, things aren't getting warmer, but the rate at which things are changing is faster because of these bigger thermal gradients we see. And then each one of these lines is where you have constant pressure. So the red line, that's a ridge, if you will, of high pressure. This guy, these gray bands are a cold front moving across due to the pressure gradients. And that, as I said before, that's associated with a low zone, a low pressure zone. All right. Now, so that's kind of global patterns. These are more local patterns that you're likely to see near a body of water. For example, as the sun comes in, this is during the day, obviously, when the sun is shining, you get the land, the surface of the land can heat up very quickly. That's going to drive warm air up. It's going to suck cold air in off the ocean. So at night, once the sun goes down, the land mass is going to cool more quickly than the water mass. So therefore, the relatively warmer water blows the air in the other direction. You can see the boat sort of head in the other direction. You get these other circular patterns. You see that too in the mountains. In here in Missoula, living in the Rattlesnake, for example, where I do. This phenomena is not quite as apparent, but basically you get air blowing up the mountain during the day, and you have it coming down the mountain at night. This is pretty obvious to me. I can almost stand at my front door windows, which face up the mountain, and feel air coming in at night and blowing right out the basement on the downhill side. It's pretty evident at night. These sort of warm pockets releasing themselves and doing this sort of double circle. And you could imagine this being any one of a number of valleys right here in Missoula. Okay, now we did this calculation a little earlier. Hopefully you got the visual on where I was going with that. So if it takes air 1 second to move the length of this 10 meters, then obviously the velocity is 10 meters per second. The authors have used a uppercase V for velocity. I prefer to reserve uppercase V for volume and use a lowercase v for velocity. And that's more of a standard convention. All right, let's take a break there and then we'll get into 7.3.